Now let's go to the last part, that is nothing but the series combination and parallel combination of a cell. It is very easy for this. Don't make it don't think it that it is difficult. Okay, think that it is very easy and it will be easy there. Okay, now as I told you that in the case of combination of resistors, two electrodes, two connecting leads are there for each and every of these cells. You may be taking that as positive electrode, negative electrode, so it will have two connecting leads. Okay, so if these different two or more cells if connected one after the another, okay, then we will call it that combination of cells as series combination. Now from positive terminal, negative terminal, alternately you have to connect it. Okay, this is the negative terminal of one cell, you need to connect to the positive terminal of another cell. The negative of this cell will need to connect to the positive terminal of the another cell alternately, negative positive, negative positive, negative positive, so on, like that. So if they are connected in this way, then we call it those two or more cells are said to be connected in series. Now as I told you the peculiar properties, when the current is flowing in such type of combination or connection, what we call a series connection, then what happens, same current will be flowing across these different cells. Okay, your EMF of the battery, right? The EMF of battery is the sum of the individual EMFs. Okay, whatever the potential difference across these two ends will be equal to the sum of the EMFs here, E, E, E. Suppose if these are taken as of the same or similar cells of whose EMFs are E, 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 internal resistance also same, R, small r, like that, then this EMF will be equal to, the total EMF I mean, will be equal to E1 plus E2 plus E3. Here we are taking up what, similar cells, so your E will be all same. So we need to find out what is this total current. We need to try to express this total current in terms of this E and R. Okay, and we need to see whether the current is dependent on the number of cells. Now let's take it that such similar cells are connected in series. How many cells? N cells. So such N cells are connected in series. Let's take it, of whose EMF of individual cells is denoted by E and internal resistance by small r. Okay, and it is connected to the external circuit, say R. Right, so the total EMF of these different cells connected in series, now we will call it as battery. So the total EMF of this battery will be what? It will be equal to NE, where N is the number of cells connected in series. Okay, and we have taken that these cells are similar, or you can say, or you can call them as identical cells also. Okay, so your total EMF will be NE. If you are having only two cells, then it will be 2E. If you are having three cells of whose EMF are E, then it will be 3E, or thrice E you can call it. So let's take it that there are N cells connected in series. So what happens, total EMF will be equal to what? NE, right? And the total internal resistance of all these cells connected in series. Now we know that equivalent resistance for connection in series, okay, connection of those resistors, then the equivalent resistance will be equal to the sum of the individual resistors. Okay, if you are having N cells, then there will be N small r's connected in series, right? So its equivalent resistance will be what? R plus R plus R, so on up to N times. Okay, for N cells. So you will get as NR will be the total internal resistance. Now total resistance will be what? Total resistance in the circuit, as these cells and the external resistor are connected in series, current will have to flow like that through this, okay, resistor, and then it will go to different individual cells. So they are connected in series, same current is flowing across this external resistor, internal resistances, right? So what happened? Total equivalent resistance will be what? NR plus capital R. This will be the total resistance of the circuit, total what? Potential difference of what? The cells connected in series. So what happen? Your current will be equal to total EMF, or rather total potential difference to the total resistance. When we try to find out I will be equal to what? V by R by Ohm's law. V means what? Potential difference. Okay, or rather you can call it here as what? Potential difference, no doubt, because current is drawn from here like this. So your total potential difference, that will be equal to your total EMF, right? That potential difference across these two ends will be also the potential difference here. Got it? So what happened? Your current I will be equal to what? NE. This is the total potential difference divided by the total potential difference divided by the total resistor. Okay, total resistance you can call it. So this is the relation for the current flowing through this circuit. So we need to see this current, whether this current depends upon the number of cells. We need to see if it depends upon the number of cells, and then that condition will be profitable. Now I'm going to tell you that condition. Okay, suppose let's take a situation that this external resistance is very much less than the sum of the internal resistances of those cells. Okay, that means if your R is very much less than the total internal resistance of the cell NR, then what happened? This R is so small in comparing to this NR, so this R can be neglected, and the relation will be equal to what? I is equal to NE divided by NR, right? So when you cancel this N from the two, then what happened? You will simply have what? Get as E by simply small r. That means your total current will be equal to E by R. Got it? But this expression is independent of the number of cells in. Got it? There is no n, small n here. So it will be equivalent to the amount of current flowing or given by a single cell. Got it? By a single cell. So it is independent of the number of those cells connected in series. If you are having thousands of cells, such identical cells connected, then what happen? If this is the condition, that means external resistance is very small when you compare with that of the internal resistance, then it will be just equivalent to the current, okay, given by a single cell. So it is of no use whether you are connected 1000 cells or whether you are connecting one cells. Okay, so that one, what happened? If this is the condition, that means when the external resistance is very much less than the total internal resistance, then this type of connection, that means series connection of resistance, is not profitable. It's of no use, I mean. But the other condition, when this internal resistance, the total internal resistance, is very much greater than this what? External resistance, that means when NR is very much less than that of the external resistance R. Okay, when you compare these two, if this one is greater, if external resistance is very large when you compare with this NR, that means this is very small, R is very large, the sum of these two will be nearly equal to what? The larger value R, capital R. So what happened in this case? It will be equal to what? N times of E by R. So E by R is nothing but this is what? The current that is produced, okay, by the total what? Cells connected in series will be equal to what? N times of E by R. So this is the maximum current that can be produced by those cells connected in series. And now a factor N is there. If you are having 2 cells, then this will be 2 times. If you are having 3 cells, then this will be 3 times. If you are having 1000 cells, then this N will be 1000. So it depends upon, it means this current depends upon the number of cells connected in series. So this connection of series is profitable, useful when the external resistance is very much greater than the total internal resistance of a cell. Got it? It depends upon this n. Got it? So series combination, you need to note down this point, that series combination or connection of cell is useful or is applicable only when the external resistance is very much greater than or larger in value than that of the total internal resistance. Got it? This will be opposite, just opposite in the case of parallel connection. Let's see the last topic of today's class. Okay, cells in parallel connections. When these positive terminals of those cells are connected to one point, negative terminals of these cells connected at one point, then we call it such type of combinations as what? Parallel combination. Now, as I told you, the peculiar properties in the case of series and parallel connection of resistors, okay, those peculiar property will also be there in this parallel connection of cells also. Okay, same potential difference will be there across these different what? Battery or different cells, I should say. So as these are of identical cells, what happen? The potential difference across these different individual cells will be what? It will be having the same EMF, E. Okay, the potential difference here for this, it is E, no doubt, here also E. So this E will be the total potential difference, okay, or EMF you can call it, and being connected in parallel. Okay, the internal resistance, the what total internal resistance, you can take it like this. Let's take it that 1 by R P connected in parallel. Okay, R for equivalent resistance, P for connected in parallel. Let's take it that these are the individual resistors, they are connected in parallel, so it will be equal to what? 1 by R. Okay, 1 by R. If you take it this as a first resistance, then for the second resistance also you have to take it as 1 by R like this. Got it? For a third resistance also you have to take it 1 by R, and such 1 by R you need to go on, okay, as long as how many number of cells you are connected. Got it? You have connected. So suppose here in our today's class we have taken that such n cells are connected in parallel, so we need to go n cells. Okay, first, second, third, then you need to go up to n times. So if you are having only 2, then it will be 1 by R plus 1 by R, that means it will be 2 by R, right? If you are having 3 cells, then it will be 1 by R 3 times, so it will be 3 by R, right? So your equivalent resistance RP, if you take it this reciprocal out again, then it will be equal to RP. So if you are having only say n cells, then it will be equal to, this will be equal to what? N by R. 1 by R. When you keep on adding to n terms for n cells, then it will be what? R by n by R, right? N by R. So if you take the reciprocal, then it will be equal to what? R by n. Got it? That is what I want to explain you. So your equivalent resistance of those internal resistance connected in parallel will be equal to what? R by n. This R by n, okay, it will be replaced by a single resistor which is equal to RP. So that RP and this external resistance R, they are connected in series again. So your total equivalent resistance will be what? This RP plus capital R. You can call it this as R by n plus R. Now we need to find the current, and we need to see whether that current is depending upon what? Your number of cells or not. If it doesn't depend on the number of cells, then it will not be profitable or useful. If it depends on n, then it will be profitable. Let's see, your current I will be equal to total EMF divided by total resistance in the circuit, right? Now in this case, what happened? If your this r by n, here it was r by n, okay. After doing that simplification, it goes here like this, okay. R plus r by n, if you take it the LCM, then it will be what? It will be r plus nr divided by n. Got it? That n goes here. Clear? Should I show you that one also? Okay, let me show you. Now this, what I will be equal to what? The total EMF is what? Total EMF is E, right? Total EMF is E, and total internal resistance is what? R by N plus R, right? So if you do the LCM for the denominator, then it will be E, right? Then LCM will be N, and this will be R, small r, plus NR, right? Got it? So your N can be brought in the numerator, then it will be NE, what is having here NE, okay, plus R plus NR, or you can write NR plus small r, okay. That is what I have written here in a very short way, so you can see that one. Let me remove this whatever I have written so that you can see it very clearly. Yes, like that. Now see, so what happened when these NR and R, we are going to compare these two, or rather R by N with the capital R. Got it? So if when you compare these two, if these R by N is very much greater than this R, okay, when R by N this is very much greater than R, then it is profitable. Got it? N by R. This is just the opposite. When the external resistance was very much large with compared to the internal resistance, in the case of series combination, it was profitable, right? But in this case, let's see, instead of saying in that way, we can also say that if R is very much less than R by N, got it? Or rather, if you take it R very much greater than R by N, you will have it like this. Got it? If external resistance is very much large than that of R by N, that means total internal resistance, then it is of no use. Why? Because there is no factor N here in this, in the expression or in the equation of current. But when R external resistance is very small when you compare with that of a total internal resistance R by N, got it? External resistance is very small in comparing to that of total internal resistance, then I can be expressed as N times of E by R, E by small r. That means this will be very small when you compare with this R, okay? That is the meaning for this one. Got it? If external resistance is very small with in comparing to the R by small n, that means your NR is very small. So what happened? It will be equal to what? NE divided by R. Got it? So as the factor N is there, so it is profitable. If you are having two cells, then it will be twice. If you are having N cells, then it will be N times. So what happened? Your parallel combination of cell is useful or profitable only when your external resistance is very small in compare with that of a total internal resistance. Got it? With this, we will come to the end. We come to the end of our today's class. Okay, thank you.